Okay, I think let's just get started just partly because I know Tim, and so I know that short on-time presentations are potentially not in your like list of strengths. You've got a lot of other strengths, Tim, though, so it's okay. So today, how it's going to work, I'm just going to say a couple of words to begin with, and then Tim, I think, has got a short presentation, and then it's going to jump into some more hands-on coding. And so Vanessa will also be moderating the questions sort of during and afterwards as well. So before we get started, I just wanted to say a couple of things about the website and the community and stuff. So if you're on Twitter, you may have seen, but if not, so we have this, we've collated this list of presentations that are happening at IPC. Is it like, it's in a couple of days, right? So we got everyone to sort of self-report whether they're doing a formal demography related presentation, and we made them into a little list. So if you're interested specifically about formal demography topics, you can go to that list and have a look and check out what's happening. So there's a link to that on our website. There's a few more details on our website as well. Vanessa put together a really nice schematic about sort of broadening a bit more what we want to achieve here in terms of 3 sort of main goals. So check out that as well if you're interested, and we can have a chat about that next time, I think. You may have noticed we have this logo, which is very fun, and I'm getting hex stickers printed. So because why else do you start a group if not to have stickers? And so what we'll do is we'll send a couple of stickers out to everyone who presents or volunteers in some way, and also hopefully PAA and EPC are going to be in person, and if so, we'll bring them along there. And so if you're coming along to those meetings, you can come and bug us for one if you would like one. And then just a couple of like little quick, just to set the scene for the next couple of meetings. It looks like in January, we're going to have a sort of my favourite formal demography paper discussion with Roland Rao and Annette Bordish, which will be really cool. And then in February, it seems like we might have kin-based methods, new developments in kin-based methods sort of talk and hands-on demonstration. And I should say that if you are interested in presenting your work or doing something else in this working group, you should definitely get in touch with one of the organisers, me, Vanessa, or Rio, who's not here today because it's a ridiculous time in Tokyo, unfortunately. Okay, so now let's get started. So I'm going to introduce our speaker. It's an absolute pleasure to introduce Tim Rife to the working group today. Tim is a research fellow at the Basque Foundation of Science and a visiting professor in sociology at the University of the Basque Country. He holds a PhD in demography from Barcelona. He did a postdoc at Berkeley working on the Human Mortality Database. And then he was a research scientist at the Max Planck Institute for Demographic Research for a number of years before living the dream in the Basque Country. Sounds very idyllic. Tim works on a range of different problems. One thing he's interested in is using indirect and decomposition methods to understand health and mortality disparities. But Tim really has an impressively far-reaching set of contributions to demography. So, for example, as well as contributing to recent work on understanding the impact of COVID on health and mortality, he coordinated the creation of an open source, free open access database called Coverage, which provides up-to-date information on deaths, cases, tests, and vaccinations. He has done a lot of work on data visualization, including teaching some of those skills. And also some of his formal work thinks about different concepts and how to unify different concepts of demographic time. Tim also leads the development of demo tools, which is an R package to make implementing demographic methods easier. Those of you who know Tim know that his enthusiasm for everything demography is somewhat infectious. I love bugging Tim about all sorts of problems because he's always so supportive, even if those ideas are ridiculous. And he always has a really interesting perspective and really interesting take on like what I could try and other stuff. So thank you so much, Tim, for coming along and talking to us about decomposition methods today. I'll hand it over to you. I think I made you a co-host, so you should be able to share your screen and everything.
Yeah, thank you for those very kind words. Thank you. Hi, everyone. I'm Tim, and the topic of today's presentation, it was spontaneous, and we're trying to be responsive to the kinds of feedback people gave in the previous meeting. And if I understand correctly, right, there's going to be some bifurcation in the different functions of this group. Do you perhaps want to say a word on that? So in this particular one, there's going to be kind of a how-to, but other topics may vary, I guess. Perhaps you'll want to stay tuned for that sort of information. But I'll go ahead and share the screen. This topic is also kind of ad hoc. We were just brainstorming and we said, okay, well, this is a commonly requested thing, and so so I hope it's interesting to a good number of you. So before getting into coding, I wanted to talk in general about demographic decomposition, because every time I have to do something like this, I realize like how big and varied it is. And so for the sake of abstraction, I've gone ahead and at least I want to share what my mental model is for categorizing the different kinds of demographic decomposition that there are. And maybe before I do that, I should say in general what it is. So decomposition in demography is, it's a broad family of approaches that you would use to try to explain a difference in some synthetic measure usually. And there are different ways in which that can be done. But the general idea is you should be able to break a difference down into a bunch of components that add up approximately or exactly to the difference. And in so doing, you should be able to explain the difference and say, this much of it's due to this factor or that other factor. And that will become clearer with some pictures. Oh, yes, but before we go, this talk, I'm gonna show graphics from other people's papers, and I didn't make a diligent bibliography, but they are linked. But I guess for you to enjoy those links, you're gonna wanna actually be able to get to the presentation. So the important, perhaps somebody here, let me, I'm gonna copy this. No, go back. Whatever, somebody write 2P88J4MD in the chat, and that should be enough, okay? To get to where I am, or should I leave it there for just a second in case somebody wants to type it?
Robert Pickett already done it, so.
Okay, sweet, thank you, Robert. Right, so I'm gonna try to break down decompositions into three very broad categories that they're not also perfectly mutually exclusive. But this first kind I call bespoke decompositions. These are once-off neat ways to think about breaking down a synthetic measure that do not merely distill down to asking what is the contribution of each rate or parameter, but rather what is the contribution of broad, abstract, other ways of summarizing the same data to the synthetic index. So in the left here, this is a paper from Quinn and Canudos Romo, where and the thing about this family of decompositions, it's also usually exact, right? So within here, we would include within decompositions. They do what they do, and they do it very well, and they are exact. But they are not about asking what is the contribution of this or that rate, right? Or this age or cause or something like that. So the one on the right is a paper from Alison van Raalte, breaking down a difference in a life disparity measure into the contributions above and below a particular threshold age, which is itself a function of the life table. And the one on the left is doing a kind of shape, location, scale sort of decomposition. Right? We can understand these are different ways of capturing some characteristic of the shape of mortality, but they're not just a component-wise drilling back to the rates. I'm sorry if that's not clear, but this is like a basket, and the thing to understand is that these, and then there are lots of these. Maybe we should make a list. Anyway, this is maybe the most creative kind of decomposition. This and another. Okay, so the other kind, the second kind, I'm going to call direct decomposition, but really you could call it generalized decomposition or exact decomposition or something like that. And the idea is to drill back an arbitrarily calculated synthetic index to map it back to the actual parameters that are used to calculate it. And then you can summarize those however you want. And so in this picture on the left, Rosie Seaman summarized the changes in a slope index of inequality and drilled it back to age and cause. And those are just binned up in different ways in that visualization on the left. In the middle one, was it Martin Kolk and Yashin Chi are looking at pension inequality in Sweden and asking how much of it is due to what they make when they're retired versus mortality differences. And in the third one, this is like a parody decomposition of fertility chains from Eva Bojan. So again, you can get the links to these things inside the presentation. Point being that there's a one-to-one mapping of the parameters you need to calculate it, ideally independent parameters, and the result. Okay, so direct, and then indirect. This is also a very creative one, but here these are various pictures of different ways of breaking down. I'm sorry that most of these examples are mortality. It's just that's what I have in my head. Okay, but this is equally rich for fertility. I just don't know that literature quite as well. But these are different ways to schematically summarize a mortality curve, basically, either looking at the distribution or the rates in additive ways. So for example, in this one on the left, we have different mortality model parameters. But the thing is that model doesn't exactly describe mortality. It approximately describes mortality. And likewise, this bottom figure from Ugo Filippo Bassolini and co-authors is like a shape scale sort of thing. It's approximate. The one in the upper right-hand corner is breaking down mortality. It's a lot like a Heligman-Pollard. Let's see if we can get log mortality to add up to different schematic components that we can give memorable demographic names. Right? This family of decomposition is typically not exact, but it usually gives really good insights. Well, they all do, right? Now I'm going to go ahead and give my hot take. Before talking about coding aspects, I don't want to get hung up on this because I want to spend more time in our studio. But I suppose that this family of decomposition is the one that's most useful if you want is to be able to do something like target interventions or know which parameters actually have the most leverage, that sort of thing. This one increases understanding maybe more. That's not to say those are mutually exclusive categories either, okay? Now, as for coding, the coding requisites. So when it comes time to actually implement these things, one thing that you cannot do without is being able to write functions. I'm sorry, I'm premising this all in R speak, but it would be the same in Python or in MATLAB, and I imagine also state out. And honestly, I don't have a good survey of what language environments people use, but I'm going to try to use a flavor of R that I think is going to be generally intelligible, even if you use those other languages. So one of these bespoke decompositions, if you want to implement it, the kind of coding that you need to write is exactly the same as the kind of coding you would need to write to calculate the measure in the first place. It's just to do a bunch of steps and calculate the result. That's hand wavy, but I'll show it too. And the second kind, a direct one, is very similar also. So that doesn't require further language. But the indirect kind of decomposition, the really, really creative kind, that requires optimization as well in statistics. And so that's very involved to implement usually. It's another layer of coding that's required in order to get the job done. So in the examples, I'm going to focus on the first two kinds and try to put special emphasis on the direct kind of decomposition, because what I think a main take-home message that I want to be is that if you can write a function that calculates an index, whatever it may be, as long as it's a direct mapping in the strict sense, that this set of parameters leads to this and only this result, then it's decomposable, and it does not matter how complicated your function is. Okay. So I wanna try to show how that works. Okay. And the code that I'm going to be working with is located here, and perhaps somebody could put that in the chat too. I literally just put that in that repository like a second ago. Okay, can I open up my RStudio now? Is that in the chat already? Sorry, I don't get the notifications.
Yeah, it's there.
Okay, cool. So if you actually let me go to here. This is that repository. What you see in there is a little bit of example data that I shamefully ripped from the HMD. This file, tutorial.rmd, that's the one that I'm going to be working in now. Okay, that's an R Markdown file, so it has both text and code. If you're not familiar with that, I'll point it out. And this HTML version, I guess if you were to download this, you could render it in a browser, and it would be nicer looking and easier to look at. And as I wrote here, I probably should have just made a pull request to the repository that the organizers set up, but I haven't done that yet. But we can do that later, right? So if you have RStudio, there's two things you could do to get this and work with me now, right? One would be to download the zip, to unzip it, and to open that project. There's an rproj file in there, okay? The other would be to copy this URL and go to RStudio and import it as a project. So in a very hand-wavy way, if you had that URL, this one right here, just press that button, you would go to File, New Project, Version Control, if you have Git installed. So this is even a smaller subset of the people in the call. And then choose Git and paste it in there. And if you click Create Project, then you'll just get all that stuff, and it'll open up right like I have it here. Okay, so now I'm just going to take, I don't think it's required to, I'm not going to assume that everybody's working along, but I'll narrate this as best I can within the time limits. And first I'll make it a bit bigger, I'm sorry. Appearance. Is this better? I think this is better, right? Okay. Just in case somebody's on a small device.
Tim,
So, yes.
Sorry, just before you get to the hands-on, I would like to add this question from Jessie Naido, just because maybe you keep this in mind when if you want to discuss this or an hour later, which says that if possible, can you comment on the relationship between these decompositions and some model of causality for the processes under study? For example, what is the counterfactual in a statement like X% of the change in this measure is due to the contribution of group G?
Now that kind of question comes up from time to time. When we calculate an index, usually that's a deterministic and direct mapping of the parameters to the result. And the question of how much leverage each parameter has on the result is kind of a mathematical one. And if you can imagine, then the world is like literally and completely described by whatever the model is that produces the results from the parameters. If that were the case, then it would be causal. But it's not, because all of the things that we calculate are very far from, right, the complicated world. I mean, is that getting, so like in that very hermetic sense, decompositions are causal, I think. But that I don't think they're practically, I mean, and I wouldn't try to use them that way. You would need a very, very rich setup, I think, right, in order to make a statement like that. And I think somebody else probably has thought about this a lot more than I have, somebody in the room right now. So perhaps they could offer their thoughts. Okay, right. So okay, so the main thing to get over for implementing any decomposition method is the need to write functions. And so I'm gonna start by showing the basic anatomy of writing a function. Then we're gonna write some teeny tiny life table functions that are gonna help us do the work we need to do later. Okay, so we're gonna build into it. The basic idea is that to make your own function in R, you assign to it. And so the name of this function, this is the assignment, is going to be function name. And it's a function because this here. And whatever's inside the round parentheses are the inputs to the function, which we call arguments in R. And whatever's inside these curly braces is the guts of the function. It's what's doing the work. And it can be small or large. It could be one step or it could be many steps. And inside here, you can do whatever you want. Whatever happens in the function stays in the function. The only thing that gets out of there is the result, okay? And it can be ugly or it can be parsimonious. It can be as you please, okay? That's the nice thing about functions. And then you can use it, you use it like so. So this would be just like if this was math, I would say this was F. Now, right? So let's see here. This is hypothetical, and then you would just get your little answer like that, okay? All right, so now another thing, and this is just so that we don't have to like install as we go. Let's just get this over with right now. If you're working along, go ahead and install the packages that you see here. 3 of them are sitting on my GitHub, and if you want to install them, if you're on Windows, you're going to need to install this other thing that you'll see linked in the tutorial. So I'm going to, I guess, for the sake of speed, not try to troubleshoot this right now, okay? But I'm happy to if you leave an issue on the repository or send me an email, okay? So let's get all of these packages loaded that we're going to use. Okay, this is the example data that I prepared. you'll see another file in that repository called test.r where that thing was created, if you're curious. And if you want to see what it is, it's basically this. So we have male, female in total stacked in its HMD data, ages 0 to 110. Mortality rates, I put them side by side to make the following a little bit easier. Rates and population exposures, which actually I didn't end up using. Okay. So the first thing we're going to do, so I want to, first I want to do is show how to code a bespoke exact decomposition, namely the Ariaga decomposition. This one is taught quite frequently. It can be implemented in the spreadsheet. That's how I first saw it. You can find it in the Preston book. You can find it all over the place. And in order to do that sort of thing, you need to have all of the life table columns on hand, or some of them, or many of them. And so these are just going to be little helper functions to turn our rates into those columns. And I'm doing this using the hackiest shorthand possible. This here is taking the way a statistical demographer would show you the survival function being generated from the cumulative hazard. And I'm just going to say, oh, my single age rates are kind of like a cumulative hazard, because that's, I mean, the thing is, each of these functions, you could replace it with your rigorous function, your MX-AX combo, or whatever proper thing you're going to do. But you know in advance that the error here is going to be less than half of a year. And we're just going to use this in a comparative way, and the comparisons are basically going to be valid. And this is way faster to write and way faster to execute than whatever the other alternatives might be. So usually when I'm prototyping something, I go straight to the hack. And then when the project gets serious, then I replace that with the rigorous thing. Okay. So this just converts MX to LX. Maybe I should show. The formula is going to be, the LX is going to be e to the, this is going to render in a second, so bear with me. From X to the, what is it? Is it, yeah. Empty? I forget. Yeah. Okay. Of H T T. And I think if I do a line break, that'll, maybe if it'll render if I do $2 signs. Yeah, there you go. That's what's happening inside of here, except for it's a total lie because those are single age data. Okay. And we make sure that it has erratics. Okay. And we make sure that it's the right length. Okay. Likewise, this decumulates that in a positive way to give us the death density from the survival function. It's exact. So if you have a good LX, then this will be good too. This is a linear approximation to get life table exposures, the capital LX one, in single age data, right? We're just going to assume it's halfway between the two exact tiny LXs. This is also the kind of thing you'd swap out with the rigorous one. This is that kind of confusing to everyone TX calculation. So you want to integrate LX but top down. And so we're just going to use that to get TX. And now you can convert LX into EX, so life expectancy, just following those last key steps of the life table. So this is this is like skipping some of the important steps of the life table, but we're just going to get straight to life expectancy here. Now the ingredients, right? So anyways, here, let me. Load everything up to this point. So these are like homemade homebrew functions. So to use them, I mean, there's lots of ways you could use them. You could use them in the base way. So you could imagine you have a vector called mx sitting around. You can just feed it to that function and get the result. That works. Okay. You can pipe it through the different stages. So if you like to code in the tidyverse way or this more contemporary way of coding, you could send this vector to this function, get that result, and send it to this function. That works fine. Or if you are really in more of a tidy pipeline kind of way, which is what we're going to try to use more as we go, you could just use it directly inside the data object that you happen to be working on. If you haven't seen this construct before, what's going on is the following. This data set, ES, it has 3 subgroups in it, male, female, and total. I can declare groups on it, which turns those into discrete subsets. So now you can imagine them as in separate boxes that don't affect each other. And now we can create this new column on the data. So mutate doesn't affect the number of rows in the data. You can either change a column or you can add a column with it. Okay? You'll see me using this a lot in a little bit. Okay, so now the Ariaga style, let me see if I can get this to render. There we go. The actual formula, it's one of these like, oh my God, notation kind of formulas. And it's the kind of thing where you can break it down into smaller pieces. And so I guess to implement this in R, there's different ways you could do it, but I think the key thing is to think about it literally, as in like this here, think of it as a whole vector of LX for 1950, and this is a scalar, but we don't need it because our radix was 1 in the first place. And so we're just going to be taking ratios and sums and things like that, and all right inside of a mutate call. So the code to make this, it's going to be taking that first data object, declaring the groups, creating each of these values that we need to calculate the Ariaga decomposition. So that's LX for both subgroups, capital LX for both subgroups, and TX. I guess we only need it for the 2000 subgroup, whatever. And the idea, if you carry out this decomposition, then you get the age by age contribution to the change in life expectancy. And there's more than one way to do this. This isn't the only way. I think the method was proposed by more than one person right around the same time. So, so let's just go ahead and do that. So in this first piece of the pipeline, in a single mutate call, one after another, this is making those requisite columns that are required for that formula using our own little functions that we just made. Okay? If this is a lot right now, then it's the kind of thing you can step through slowly as you go on your own machine. Okay? We could continue straight into the decomposition, which is here, but I'm just setting it aside so that I can talk about it separately. Okay, I'm going to scroll up to that formula so you can see it. So I'm just going to refer to these things kind of verbatim. Okay, and you see that we have, in some things, we have age X, and this X plus N, that means the next age group. So the trick to do that, I'm going to use a function called lead, which is just a negative lag. So let's scroll down to the actual where the decomposition happens. Instead of having one big messy formula, I'm going to break it into the left side of the sum and the right side of the sum, the indirect and the direct effects, the other way around. So in the formula, this is being divided by L0, but that's not necessary because we have a radix of we have a starting population of 1 in this life table. And then here those formulas are very literally. So we have the direct, the indirect, and they add up to the total. So this is that delta that you saw in the earlier formula. I think you'll have to refer to these things in your after this Zoom probably. Right, so there it is, calculated. We create this object here that you can see. We have the direct, the indirect, and the total by age, and those ought to add up. So this this total column in each subgroup, it should add up to the difference in life expectancy, right? So these here are the those are the life expectancy differences from the Ariaga decomposition, and we have our own little life expectancy function. So we could just pick off that value and verify that's exact, and you get the exact same results. So Ariaga is exact. Okay, I call this a direct decomposition. It was even though it's not a generalized decomposition, it's as direct as they come. I'd like to give a footnote. This is the appropriate time. It would be nice if somebody invented a way to propagate the Chang uncertainty through the Ariaga decomposition to put error bars on everything. Can somebody invent that, please? Thank you. Back to coding. Okay. Right. And there, to clarify, so, I mean, the results turn out to be basically, it's all infants because we're comparing 50 years apart. That explain that difference, okay? The other way, and I think the way that you should do this, instead of doing it the way I just did, as in let's create a bunch of columns and then do a bulky composition calculation inside of a pipeline, it's not so portable. You'd have, you know, like, I would suggest writing a function that just does all of that and produces the result. So here is an example of that I'm not going to narrate. I'm going to skip it because I think we should get to the generalized decompositions, if that's okay. Okay, so now getting down to the generalized decomposition. General decompositions are, they're direct because they're trying to map parameters to a difference in a value for an arbitrary function, but in a way that's as perfectly additive as one could hope for, okay? I'm aware of 3 of these. There could be more, and if that's the case, it'd be nice if somebody told me. But one of them is, well, you can find this linked, basically. So there's the Horyuchi method, basically, which imagines a continuous model of change in the parameters from population 1 to population 2 and perturbs them a little bit as they go along to there. And you end up with an arbitrarily exact result, depending on how many little pieces you want to break it into. Okay. There's another one called the stepwise replacement algorithm, which turns your first parameters into your second set of parameters, one piece at a time, one element at a time. And so you have to recalculate the result that many times, or as many elements as you have. And that's one approximation, basically, of the leverage of each result. And then finally, and I saw Hal is in this call, so I am happy to stand corrected if I'm wrong, but the basic idea with so this is called life table response experiment, but it's more general than that. I think he regrets having named it that. And the basic idea is that if you have a function of parameters and ideally an analytical solution to its partial derivatives of those parameters, then the leverage of each parameter is equal to the difference in the parameters times the derivative, roughly. Right? That's the general idea. And so the approximation here is to go halfway in the middle, take the partial derivatives at that point, and multiply by the difference. And that's a very good approximation of the result as well. And if you have an analytical derivative function, it's very efficient too. These give very close results in simple things. And as things get more complicated, then I think it's worth thinking about which one you're using. But I use them interchangeably here, and we're going to compare them with Ariaga. These are all implemented in a package called Demo Decomp. And the usage is the same for each of them. And you're going to see that right here inside this call. What you need in order to use any of these functions is to write a function yourself that takes a vector of parameters and produces some scalar result. Okay, in our case, to do Ariaga decomposition starting from rates, that means we need a function that starts from rates and spits out life expectancy at birth, not the whole vector. So here is one of those. Okay, we go to MX, we get our LX, convert it to EX using the helper functions that we made above, and pick off just that first element. I know this last part here is especially esoteric, but just to keep it quick and small. Okay, so of course I have to load that. There we go. So that works, okay? I think actually for this code to run, I need to select that function that I made above. Give me 1 second. There, I got it. All right, so here we are. I'm gonna group by sex, and note that this is another reason why I wanted those parameters to be side by side in that data structure. I know that's otherwise kind of awkward. So the functions that those are implemented in are called Horyuchi, stepwise replacement, and LTRE, and we're going to compare them with the direct Ariaga. The first argument to any of these is going to be the name of your function. Okay? Imagine your function has lots of different kinds of parameters, then you should figure out how to stack them and then make use of them in the function. It might require a little bit of bookkeeping, and I guess it's on me to add an example of that here. But in this case, we just have one vector by age. We don't have like age and cause, although it would work. And then you give your first vector, your second vector of parameters. The Horyuchi model wants to know how many little steps to break the problem into. The stepwise replacement algorithm wants to know kind of how do you want the replacements to work? What order should they go in? And the life table response experiment, you can either write yourself an analytic partial derivative function, or else it's going to use a numerical approximation inside using a numerical derivative. So let's just get our decomposition results. The one that's taking the long is this one. Let's just let that compute. The other ones are pretty quick. Okay, that's done. And if we compare them, oh, right, here we go, we get the results. So this is the sum of the delta, right? Of the age-wise wedge components. And eyeballing this, the numerical derivative function failed terribly. However, this is one where there's hope of writing an analytical solution, because that's the kind of thing you can look up, of mapping a change in MX to a change in E0. So this could improve a lot, and that's on us to do that. And the other ones are very comparable. You'll see the sums for the stepwise replacement one, and it's and because it's Andreev. The sums for there are always exact, but element by element, the values can be different. Okay, and we'll visualize that and see that they are quite close. And yeah, again, the residual for the life table response experiment one, the blue line, it's my fault for not writing an analytical derivative function, okay? And this tutorial has one more thing in it that I think there's not time to do. I think I should stop now for the sake of punctuality. if there's one thing that I would like to emphasize, though, is that these generalized decomposition methods, they're very comparable and they really are trying to do very similar things. And actually, if you look under the hood, they're all very related to one another too. For the arbitrarily complicated thing that you're doing, like that might be a good way to start, right? Rather than like deriving a new decomposition method. And if you do derive a new decomposition method, that's a direct one. It's always good to compare with these. Okay, and that will conclude the code tutorial. And I apologize for the speed, but I think it was important to compare with Ariaga. So
we already knew.
I'm sorry?
That, just joking, that we already knew that the time constraint was too,
well,
too constrained.
This content I deliver in a summer course, but it's 4 hours there.
I know, so, just joking. It's very complex. Thanks so much. I just wanted to take the opportunity before just to do some questions that were raised while you were talking in the middle. So one by Corey Sparks. So if by generalizable, do you mean that these can be applied to any arbitrary set of rates? And also from Gilvan Guedes, can you change the numerical method in the Coswell function when there is not an analytical solution for a more generic decomposition?
Yes, Corey, the kinds of, so it's general in the sense that it doesn't have to be rates, and it can be any rates, and it can also be any function of those parameters, right? It's like way general, as long as the things that are parameters are things that have leverage on the result, then it makes sense to include them in that vector of parameters. So some examples of weird ones is, like we had mortality rates by age and cause for deprivation deciles in Scotland, and said, okay, let's calculate some life table disparity thing and then look at a slope index of inequality over it. And like, that's so many stages of calculating and estimating, right? But that was all inside one function, which started with those rates, right? Those very structured rates. And then that just would plug into any of these three methods. Right? If that helps sort of like shed some light on how general is. And the other one was, yes, you can swap out. So the idea is we send those generalized functions a function that we write. You can write your own partial derivative function or give it a different numerical solution also. Yeah.
Also, Monica had a question. Given the generalizable ones are pretty similar under the hood, do you recommend one over the others? I've seen Horyuchi applied a lot lately, but maybe that's just because I'm reading a lot of the same papers.
Well, if I had an analytical partial derivative function, I would go to the life table response one, but I'm not very good at making those and deriving them. So so I fall back to Horyuchi usually for that reason, but there's a penalty in that it can take a long time if you want a really exact answer or if you have lots of parameters. And the stepwise one is in between those in terms of how fast it is, but I haven't wrapped my, and I go to the Horyuchi rather than the stepwise one because I can't really wrap my mind around the leverage of this idea of which order you swap out the parameters. And I don't fully understand yet the leverage that it can have on a result. So for simple things, it doesn't make much difference, but for a complicated thing, like a multi-state life table or something like that, then I would go straight to Horyuchi or the LTRE.
Cool, thanks. Yeah, I've only ever, out of those three, I've only ever used Horyuchi, and I don't know, I find it intuitive, but as you say, it's slow. As soon as you start like, oh, I could also decompose by this, and oh, I should add more cause of death groups, and then it's just like, you know, waiting.
And you start wanting a server, yeah.
The fan on my computer is just going over time. Yeah.
There's an aspect of the Horyuchi method that sometimes is a hang up for some people. If you read the paper, the example that they give is a linear change from the first parameters to the second one, but you can engineer your way out of that. If your function starts with, say, the logit of those parameters, then the linear mapping in your original scale is no longer linear. So you can work like that also. So the thing to understand also, the result of any of these, it's on the scale of the difference, right, that you're calculating in the first place. It's always on that scale. So it doesn't matter what transformation of parameters you send in.
Any more questions, anyone? Still have some minutes to bother Tim.
Is anybody up to the challenge of propagating Chang's?
Yeah, that's a good. So we're gonna set within the group maybe the challenges of millennia.
Put a bounty on
it. Yes. Like they have for solving hard mathematical issues. We're gonna put the challenges of millennia, demographic challenges of the millennia.
So if you wanted to put uncertainty on any of this, you're in a bit of a bind. You're always going to want to be biased towards the fastest one. And then in that case, that's the Ariaga one itself, not these generalized ones. But for your random arbitrary problem, you're going to end up having to bootstrap or something. So so there really is a trade-off that becomes important. Yeah.
I can offer stickers to whoever wants to have a go at trying.
Free stickers.
I'll simulate the uncertainty, and then whoever can derive it, approximation, or you can have as many stickers as you want.
So I have also Tim, a question from Teresa saying, can you talk a bit about what sort of decompositions are possible with the between-within decompositions? And Eddie Hasinger said, I've wondered why Xiang.
I wondered why what? Why Chang?
Yeah, why Chang?
Oh, or binomial, or low, or any of the others that because that's the common analytical way of doing it, I guess. Yeah, the between within. So there's a new, you see it in this code. It's a new, it's experimental, but we're going with it. A package that implements life table between within decompositions for 5 or 6 different disparity measures. And it doesn't work for, say, interquartile ranges very well, or that kind of thing, but it would work for anything that's a continuous sort of disparity measure. So it works for Gini, or tile, or variance, or the mean log difference, or lots of different things like that. You can see it in the package. It's not very well documented yet, but we're working on that. Some of those were derived for the sake of that package, and others are translated from other literature, and others are known ways to do this with the life table. So I think there's probably still other within things that can be done, but I'm not super on top of that. Alison van Raalte is, though, and Christian Doodle. Well, okay, this material, I think it could live in your main working group repository. That's fine with me. I just didn't think of it before. Or you could link to this repository.
Yeah, I think maybe we'll just
link.
We'll link to it. Yeah, with the, so this is being recorded, and so we'll just put a link to the recording up on the website and also the materials. Yeah, thanks very much for making that little notebook and making that available. I think that's going to be super useful for people who are interested to go through later on.
Thank you for the invitation. And I'm very happy that this group exists. I'm now one of the people that's ended up sort of isolated. I used to always be surrounded by nerds, and you know, like, and now like, so I need y'all.
We also had this feeling, thought the group was even smaller, but then when so many people applied, we're like, okay, there are more nerds lost. We all think we're lone islands, but not that much. So yes, it's really cool. Just wanted to, there's also a question by Octavio, a comment, so maybe just to wrap it up, said about bootstrapping. I get that the thing now is to use confidence intervals for everything we do, but do you believe that it may turn the interpretations of decompositions into something really complicated, and specifically age-specific ones?
Well, I thought about that a little bit. I think if people started putting uncertainty on them, they would be tempted to start grouping ages into fatter groups because very little turns out to be significant often if you have very specific parameters, but it depends how you do it. So you could have your inputs be very specific things, and then do your decomposition and sum it or aggregate it into subgroups, and then put uncertainty on those. And so you can still, I mean, I think a lot of things we think we know maybe are not quite so certain, but I think a lot stands up though if you're willing to think about broad groups. But I think that's also kind of something that everybody should think about a little bit more.
Cool. Thanks a lot. Anyone? Any more questions? Have 1 minute. Yeah, I just, Monica, can I just mention a little bit about the 3-pillar thing? I mean, just very briefly, because I think we're trying to organize and accommodate this group in a way that we could allocate the different interests. So if you guys want to check it out in the webpage, we just added the scheme, which basically we will still have like a specific calendar, because we also know that each group, each subgroup, each pillar will probably also have different timings. So for instance, so we will have one axis concentrated on research. So specific groups of people that want to work on topics together, or that want to share resources and want to just, you know, get together into topic. This is what we called research, because we're actually advancing on something together. And then we will have training, which is what we're doing today with Tim, which is, you know, helpful for everyone, reinforces already something that we know, or puts into questions, or just introduces a topic. So it will be around teaching and training, and the other will be forums of discussions, for instance, trying to understand topics that could be like up to the current topics, for example, depopulation and shrinkage, but looking into it through lenses of formal demography issues. So we'll have this more debate, discussion, philosophical pillar, a teaching, training, and a research-driven one. And then we'll still think how to organize this, but you guys have the mail list, and you can also contact us so we can set up these groups. And they will have a certain degree of autonomy, of course, and you can also engage in one or the 3, it doesn't matter. It's just to organize, because I know some people will be more interested in like focusing on the research and not so much on the training, and vice versa. So just to let you guys be aware that we're doing this type of organization of the group.
And this, yeah, we're still, obviously this is still very new, and we're all sort of trying to fit it in around all the other things that we're doing. So this will probably take, you know, a few months to to become clearer, but just so everyone knows that's the goal. And if you have any feedback, let us know. And also if you're ever interested in, you know, presenting or whatever, please get in touch. But I think we're after 11 Toronto time anyway, so let's wrap it up. Thank you everyone for coming. It was fabulous. Thank you, Tim, so much. That was wonderful. And see you all hopefully at the end of Jan. Have a great holiday season, and here's to a better 2022. Bye.
Thanks everyone. Bye. Have a nice weekend.
Bye. Thank you so much.